Okay, so let's carry on here from yesterday, the sample work problems. So inclined plane situation, the amount of work to pull the cart up the plane, amount of work done in lifting the cart straight up, and the amount of work done if there is a 50 Newton frictional force of 50 Newtons up the plane. And I'm hoping you must have more information than I do because I got nothing there. There must be a drawing of yours, isn't there? Is that all you have? That's everything? Okay, so the amount of work to pull the cart up the plane. So, when you lift something, just, lifting a box or whatever, you do work against the force of gravity. When you push it up the plane, do you do work against the force of gravity? Yes. All of the weight force, Joey? No. What's the force down the plane? What's the component of gravity that acts down the plane? Well, we've labeled that FD. No doubt in a future physics class it'll be labeled something else, and you'll think fondly of me and say, oh, silly Mr. Bennett calling it FD, when it's clearly this more scientific sounding thing. FD down the plane. So, I'm going to say that the required force, or freak, is equal to the force down the plane. Does that make sense? You have to overcome the force down the plane. So that's simply mg sine theta. 30, 9.8 sine of 30. I get 147 newtons. Yes, you have to solve for work, force times distance, 147 times 6, 882 joules. Okay, so part B now asks, what if you were just to lift that box, or whatever it might be, straight up 3 meters? Say it again? Yeah, we have to work to overcome gravity, right? So gravity is weight force mg, 30, 9.8. 294. Then work equals FD, 294, but the distance is only 3 that you have to lift it. And what do you get? Coincidence? I think not. Mathematics. What's going on here? Can you explain, Randy? No? The box at the top of the ramp, how much potential energy does it have? 882 joules. Does it care how it got there? No. It just knows that it's 3 meters in the air and it's got 882 joules of potential energy. Is it mind-blowing, Randy? Oh.
So when you're talking about potential, is that what we're kind of like the work?
All of the work done, remember conservation of energy must be conserved, right? So you used up 882 joules of Fruit Loops energy. You put it into the box, where'd it go? Potential energy.
Oh, okay.
Right? So, why bother pushing boxes up ramps? Why not just lift them straight up if it's the same amount of work? Less force. You only need 147 newtons here. Here you need 294. The trade-off is what? 6 meters. So you got to do 147 newtons for a longer distance or longer period of time. And if you actually do the math, the cosine and the 30 degrees and all that, then it'll all sort of cancel out and make perfect sense to you. But the easiest way to explain it is the box at the top of the ramp's got the same amount of potential energy no matter how it got there. Now there's one more unfortunate disadvantage to pushing it up the ramp, and that is friction. So in this case here, the freak is the FD plus FF, right? You need to overcome FD, and you need to overcome the friction force. So 147 plus 50. Go ahead, ask. Correct. Which direction is the FD, Joey? In the same direction, right? So, you know what I mean? Yeah, they're numerically equal, right? Do I need to explain that to anyone else? Look at the picture, right? This is the required force, right? This is FD, this is FF. Combined together, they are negative 197, which makes the required force equal to 197. It's not really a vector question kind of thing. Well, it is. I guess what I really should do is I should write F net equals F required plus FD plus FF, and the F net is 0, and blah, 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 and you're going to end up with the same thing. Right? Okay, so then do you do more work when you slide it up the ramp? You betcha. 197 times 6. We actually do 1,182 joules. Ah, excellent question. I'll sit back and let you think about it for a second. No, I'm not going to tell you right away. Brandy is asking, does it actually have more potential energy at the top of the ramp just because you pushed it up the ramp?
No. Wouldn't it just slide back down? It would need that more of a force to get over the friction.
You know what, we'll get to that. Hold on to that thought. Let's deal with Brandy's query first. Okay, so, does it have more potential energy up there? No, it does not. Does the law of conservation of energy not hold true for ramps? Of course it does. Where does the extra work, extra energy go? What does friction produce? Heat. So when you push it up the ramp, there's a little bit of heat. So you could actually calculate how much joules of heat energy is produced pushing that thing up the ramp. Jason's question was, should it not, what did you say, should it not just slide right back down? Okay. The problem there is, remember, is friction is sort of like a switch hitter kind of thing, right? It will go either direction. So as you're pushing the box, the object up the ramp, friction is down, opposite motion, but when it tries to slide down, friction switches direction and goes the other way. Right? So it could actually sort of balance up there, depending on its mass. Actually, in this case here, you're absolutely right, because the FD is 147, is greater than the friction force, it would actually slide down. Yes. Mind sufficiently blown?
So the difference between the one with friction and the one without friction, like the number
Yeah, A and C.
the amount of energy produced or like the heat produced,
Yeah.
joules that
Yeah.
Okay.
There would be, I mean, you could work it out. You would take your 50 newtons times 6, it would be 300 joules of heat energy.
Okay.
If you could somehow measure that, and you can't. I mean, it's just a temperature increase, right? You get one of those guns that measures surface temperature, and you figure it out. When you stop and you look at it, is the math hard? No. Is the logic maybe a little bit harder? Yeah, maybe a smidge. But it's really not that bad. Okay, I'll be quiet. You guys have a sheet there, and as you can see, there's 3 or 4 inclined plane questions to begin with right there. There's a few I see on the back here that talk about power. Anything that has power, you can just leave out for now. We'll talk about power on Monday.
So if it was a question like that again, couldn't we just do that 50 times 6 and add it on to the previous?
Yeah. Oh yeah, absolutely. Yeah.